This is ELC131, Circuit Analysis 1, and this presentation is on capacitance and capacitors. Capacitance, symbolized with the capital letter C, is measured in farads. The unit symbol is the capital letter F. Capacitance is the ability to store a charge. Capacitance equals charge over voltage. So 1 farad of capacitance exists if 1 coulomb of charge is stored and 1 volt of potential difference is applied. A capacitor is the electrical component that exhibits the property of capacitance. And we see in figure 1 two accepted schematic symbols for a capacitor in US drawings. And in figure 2 we see the schematic symbol for a capacitor in European drawings. Now, a capacitor is constructed from 2 parallel conductive plates separated by a dielectric. A dielectric is an insulator, but a dielectric differs from insulators in that it is selected for its ability to establish electrostatic lines of force. Permittivity, symbolized with the Greek letter epsilon, is a measure of the ability of a dielectric or a material to establish electrostatic lines of force. And permittivity equals the permittivity of a vacuum, 8.85 times 10 to the negative 12 farads per meter, times some relative permittivity value. And permittivity is similar to permeability that we discussed when we talked about magnetism. Permeability is the ability to establish magnetic lines of force or magnetic fields, and permittivity is the ability to establish electrostatic fields or electric fields. And just like with permeability, permittivity is the permittivity of a vacuum times some relative permittivity value. Now we see here a list of materials that are commonly used as dielectrics: air, polystyrene, mica, which mica you may have seen if you've traveled to the mountains. It's a mineral that separates into layers. Paper, mylar, like that's used to make balloons. Teflon, barium titanate, which is used in ceramic capacitors, and tantalum pentoxide, which is used to construct tantalum capacitors. And this list provides us with the relative permittivity values of these different dielectric materials. And this also provides us with values of dielectric strength, which is given in kilovolts per millimeter. And the dielectric strength value tells us how much voltage can be placed across the dielectric without causing conduction through the dielectric. Again, the dielectric is an insulator, and with all insulators, if we provide enough voltage or apply enough voltage across the insulator, we can rip electrons loose from the atoms and molecules and cause conduction through the insulator. Now, the equation shown is used to calculate the value of a capacitor. Capacitance equals permittivity times the area, the overlapping area of the conductive plates, divided by the distance between the plates. And if you refer to the illustration in figure 3, we can see the construction of this capacitor. And looking at the equation, you can see that if we increase the area of the plates, then the value of capacitance will increase. And hopefully this makes sense in that the larger the area of the plates, the more charge we can store on the plates. And if we increase the distance between the plates, the value of capacitance will decrease because there's less attraction from plate to plate through the dielectric material. So we look at an example problem. We're given that the capacitor shown in figure 3 is constructed from two 20 millimeter by 20 millimeter plates separated by a 6 millimeter thick mica dielectric, which has a relative permittivity value of 7. So capacitance is calculated by taking 8.85 times 10 to the negative 12 farads per meter, the permittivity of a vacuum, times the relative permittivity value of 7, times 400 times 10 to the negative 6 square meters, divided by 6 times 10 to the negative 3rd meters. And we yield a value of capacitance of 4.13 picofarads. Now I want to point out that when using this calculation or this equation, that all the distance values and the area value have to all be expressed in meters so that the units cancel, leaving us an answer only in farads. So you've got to convert the 20 millimeters to meters, you've got to convert the 6 millimeters to meters. Now let's look at construction of a couple of different types of capacitors. Figure 4 shows us the construction of a mica capacitor. And note that we have several plates of foil, these are the conductive plates, connected in parallel, separated with the dielectric mica. And they do this so that we can increase the area of the plates and still have this component in a relatively small package. Now, some capacitors are called rolled film capacitors, and we see an example of this in figure 5. And in the construction of this type of capacitor, we take two long pieces of foil, separate them with a plastic film, typically mylar, and then roll these lengths of foil and mylar up together around with leads connecting to both of the pieces of foil. And then of course this rolled up capacitor is placed inside of a housing, if you will, to form our capacitor. And again, they do this because taking these long lengths of foil and rolling them up, we get very large areas of overlapping plates, so we can obtain very large values of capacitance. Now, capacitors are primarily selected for their value of capacitance, their ability to store a charge. But when selecting capacitors, we also have to be concerned with the voltage that will be applied to the capacitor. So all capacitors will have a stated maximum voltage. This is quite often expressed as the DC working voltage, DCWV. Now, if a capacitor is used in AC circuits, we'll have to convert the RMS value to a peak value to ensure that the capacitor can withstand the peak voltage that's applied. And all capacitors have tolerance, just like resistors. Excuse me. And with capacitors, we're concerned about the temperature, the ambient temperature that the capacitor will be exposed to. Typically, capacitors can operate within a range of temperatures from negative 30 degrees Celsius to 125 degrees Celsius, but these values will vary depending upon the type of capacitor or the type of dielectric. And with capacitors, we're also concerned about the temperature coefficient, and this gives us the change in capacitance per or by a change in temperature. And typically the temperature coefficient is expressed in parts per million per degree Celsius. So let's look at a simple capacitor circuit. So referring to figure 6, we see a 10 volt DC source connected to a circuit consisting of a single pole, single throw switch, a resistor, and a 100 microfarad capacitor. Now, when we close the switch, current's going to flow through the circuit. And instead of looking at conventional current, I, flowing through the circuit, let's look at electron flow through the circuit. So when we close the switch, electrons are going to leave the negative terminal of the source and flow around the circuit, and these electrons are going to build up on the lower plate as shown. I signify these with a series of negative signs showing us that this plate will now have a surplus of electrons. And electrons will leave the top plate and flow back to the positive terminal of the voltage source. And when these electrons leave the top plate, they'll leave behind a deficiency of electrons or a positively charged plate. And remember from the first class, we talked about charged bodies. And whenever we have charged bodies, we have electrostatic lines of force created around those bodies. And the dielectric will concentrate these electrostatic lines of force in the dielectric. And that's the purpose of the dielectric, to concentrate these lines of force inside the dielectric and not let them just go out into space, similarly to how magnetic lines of force travel through a ferromagnetic material or a ferrite material. So we can concentrate this force inside the dielectric. Now, understand that no current really flows through the capacitor. We've got current flowing through the switch and through the resistor. We've got current flowing from this bottom plate back to the voltage source, but no current flows through the capacitor. But it appears like current's flowing through the capacitor because we have current through the resistor. Now, after some period of time, the capacitor will be what we call fully charged. And we can calculate the charge on this capacitor using Q equals V times C. So the voltage, the charge stored on this capacitor when it is fully charged will be 1 millicoulomb of charge. Now, we'll look again at the circuit of figure 6, this simple DC circuit. And again, current, when we close the switch, current's going to flow around the circuit, and we're going to build a charge up on the capacitor. We'll have a positive charge on the top plate and a negative charge on the bottom plate. And after this capacitor is fully charged, across the plates of the capacitor, we'll have a voltage difference of 10 volts. And after the capacitor is fully charged, the current will go to 0. So I'm going to erase that. Now, we can explain this mathematically by saying that when the capacitor voltage equals 10 volts and the source voltage is 10 volts, there'll be no voltage dropped across the resistor. Again, Kirchhoff's voltage law tells us that around this closed loop, the sum of the potential differences must be 0. So after the capacitor is fully charged, the current that flows in the circuit, I, equals 0 volts divided by some value of resistance. So we know that after the capacitor is fully charged, the current in the circuit equals 0 amps. Now we're provided with an equation that allows us to determine or calculate the instantaneous current through a capacitor. Well, it doesn't go through the capacitor. The instantaneous current that flows external to the capacitor as a function of the rate of change of voltage applied to the capacitor. Now you note that current I in this formula is denoted with a lowercase I, which means it is an instantaneous value, a value at a snapshot in time. And again, from our discussions on inductors, the D is used to denote the change in a quantity. So we have that the instantaneous current equals capacitance times the rate of change of voltage, the change in voltage over a change in time. And this equation shows us, of course, that the faster that voltage changes across the capacitor, then the greater the current flow will be into that capacitor. So the capacitive current is equal or is proportionate to the rate of change of voltage. The faster the applied voltage changes, the greater the current. The slower the applied voltage changes, the lower the capacitive current. So this presentation took us through the quantity capacitance, the construction of capacitors, and an introduction to capacitive circuits.